Hello and welcome to Doc Clay's chemistry lesson. Today we're going to be doing the subject of amount of substance, and importantly we're going to be looking at reacting mass calculations. So by the end of today's session we should be able to do the three following things. We should be able to calculate the relative molecular mass of a substance using the periodic table. We should be able to calculate the number of moles in a solid, and we should also be able to calculate reacting masses and also reacting masses when they include water crystallization calculations. So, let's get going. Relative molecular mass then. Our definition, importantly, is the average mass of a molecule compared to 1/12 the mass of carbon-12. And if we're asked for that ever as a definition in an exam, we have to include the idea that it's the average mass of a molecule compared to 1/12 the mass of carbon-12. So an important definition. Can sometimes be given as atomic mass as well, where we input atom instead of molecule. So there's our definition. What about calculating the relative molecular mass, or sometimes just called the MR? Well, the MR is the sum of, and we can use this symbol here to include the sum of the atomic masses in the molecule. So let's look at two quick examples here. Let's look at hydrochloric acid, HCl, and also we will look at methane, so CH4. And in order to do this, we just need to look at our periodic table over here. Let's do hydrochloric acid first, HCl, and we've got one hydrogen atom, which has got a relative atomic mass of 1.0, and we have one chlorine atom, which has got a atomic mass of 35.5, so our MR here is equal to 1 times 1.0 plus 1 times 35.5. I'm sure you don't need a calculator there. So our units and answer is 36.5 grams per mole for our molecular mass of hydrochloric acid. And this time for methane, CH4, we will see that we have this time the MR of 4 lots of hydrogens, which is 1.0, and our carbon this time we have 1 carbon atom, which is 12.0, so our MR here is 16 grams per mole. One other more complicated one we'll look at will be something like copper sulfate, or we might have waters associated. We'll look at that later on. Back to our relative molecular mass, and importantly we'll now move on and see mass and moles, how these two things interconnect. So we've seen that a mole is just a really large number, and we have to use a large number because atoms and molecules are really very small. How do we calculate moles from mass? Well, hopefully you remember from your GCSE studies that mass is equal to the molecular mass, Mr. times by the number of moles. So we've often described that as mass equals Mr. moles as our little aide-memoire. So we can easily use that if we look at our examples before. Perhaps let's say we had 36.5 grams of HCl. How many moles of hydrochloric would I have? Well, we would have the moles is equal to the mass divided by the MR, which in this instance would be 36.5, divided by 36.5, gives us 1 mole. Perhaps something a little bit more difficult. If we had, let's say, 9.125 grams of hydrochloric acid, how many moles this time would I have? Well, our moles would be again equal to mass over the MR, so we've got 9.125 grams over 36.5 grams per mole, and our answer to that, if we put it in our calculator, is 0.25 mole. Roll up here slightly. 0.25 mole. Now, remember, the mole is just a huge number. So having small values of moles, 0.25, 1 times 10 to the minus 3, 1 times 10 to the minus 4, are perfectly acceptable answers and quite sensible answers for the moles of a substance that we have. There we have how we work out the mass and the moles. Make sure you're happy about the rearrangement of that equation. You may have seen in the past a triangle. If you want to remember the triangle, remember it looks a bit like this, and you cover up with your finger whichever substance you want to find out about. Looks a bit like that. Let's go and look at some reacting mass calculations. And here's a question, and we're going to do all of our mole calculations in a very similar way. We're going to follow these simple steps. First of all, we're going to look at the question, and we're going to find out stuff that we know. So the first thing to do is calculate moles of a known substance. So we'll look at the equation here. We've got what mass of hydrogen is needed to react with 40 grams of copper oxide. So a couple of things to think about. We know about the mass of copper oxide, so we need to look at our equation. Here is copper oxide, and we've got the mass. So we can work out the moles of copper oxide. And in the future, I'm just going to change moles of to be NCuO is equal to, well, we're going to be using our equation throughout this, mass equals Mr. moles. And we've got 40 grams. So we've got mass over MR. We've got 40 grams divided by the MR. Well, we've got to find out what the MR is. So first of all, let's go over again to our periodic table. So we've got to find out the MR of copper oxide, and while we're here, we'll also do hydrogen. So let's start off with hydrogen, because that's nice and easy. Hydrogen, we've got 2 atoms of hydrogen, so the MR of hydrogen is going to be equal to 2 atoms of hydrogen multiplied by the MR, giving us 2.0 grams per mole. Now let's do our copper oxide. Well, we've got 1 copper atom, so we've got 63.5, and we've got 1 oxygen atom, which is 16.0. So our MR here is 79.5 grams per mole. So we can put in 79.5 grams per mole here for our copper oxide. We calculate that, and we end up with something just above 0.5 We won't round down yet, we'll use a sensible number of significant figures. We've got 0.5031 moles of copper oxide. So step 2 now is to use the mole ratio to calculate unknown moles. So if we look here, we're trying to find out about hydrogen, and we've not got any numbers. That means we've got a 1-to-1 ratio. So the moles of hydrogen is going to be equal to 1 divided by 1, which is times by the moles of copper oxide, which is going to be exactly the same, 0.5031. Obviously an easy example here, but they will get more complicated. The final step then is to work out unknown mass, sorry. And in this calculation it's the unknown mass, but in other calculations it might be the unknown concentration or the unknown gas volume. It would be a rearrangement of your molar mass equation. And so we now have the mass of H2 is going to be equal to the MR, which we worked out before, times by the number of moles. And we said the MR was 2.0 times by 0.5031, and we should get there that equal to just over 1 gram, and we'll give it to 3 significant figures. And the reason we're using 3 significant figures there is we've been given in the question 3 significant figures for the mass. So a simple 1-to-1 ratio. We're going to have a look at a slightly more complicated reaction now. Another example, we're going to do this one just a little bit quicker. So first step is to read the question: what mass of carbon dioxide is produced when 5.60 grams of butene is burnt? Butene here is C4H8 burnt in oxygen. So step 1 is to work out the moles of a known substance, and we know about the butene. So we've got moles of C4H6 is equal to the mass over the MR. We know the MR is 5.60 grams, and we will go and calculate now the MR. This time then, C4H8, we have 4 lots of carbon, 4 times 12.0, plus 8 lots of hydrogen, which is 8 times 1.0, and we end up with a molecular mass of 56.0 grams per mole, which we can use in our equation. Let's take that back. So 56 grams per mole under here, which gives us 0.1 mole of butene, which is a perfectly sensible number in terms of moles. So our moles here then of carbon dioxide, we're going to use the mole ratio. So the moles of carbon dioxide, well, we've got a 4-to-1 ratio, so the moles of CO2 is 4 over the moles of butene, which is 1, multiplied by the total moles of the C4H8 is going to be equal to 4 times 0.1, giving us 0.4 moles of CO2. The mass then of CO2, well, that's going to be equal to Mr. moles, which in this instance, I've already done the calculation, is 44.0 grams per mole for the CO2. times by the number of moles, which is 0.1. And we should end up with there 4.4 grams of CO2. There we go. We're going to move on our reacting mass calculations now to look at some water crystallizations. First of all then, let's have a quick look at what water crystallization is. It's essentially water that is part of a crystal framework, and it's normally water which is associated with molecules in an ionic lattice, but not necessarily directly bonded to them. And two classic examples are anhydrous copper sulfate, which we're used to being described as CuSO4, and then we have hydrated copper sulfate. And this has got water associated and is typically blue, and it's defined by CuSO4, and then per copper sulfate molecule there tends to be 7 waters associated with each copper sulfate. So the water crystallization, there are 7 water molecules per copper sulfate. And often we're asked to find out what the water crystallization of a given substance is, and we're going to look at how we can work that out now. So as we read through this question, we're going to just note down underneath what we know about each substance, because we're going to follow those 3 steps again that we've seen before about working out knowns and unknowns. Here we said 4.92 grams of hydrated magnesium sulfate crystal. So we know we've got 4.92 grams of the hydrated magnesium sulfate. Gave 2.40 grams of the anhydrous, that is without water, magnesium sulfate on heating to constant mass. Work out the formula mass of the hydrated magnesium sulfate and therefore the value of N. So what do we need to do? Well, we can find something out about these substances. The thing we can find out the moles of, well, that's going to be the magnesium sulfate in this instance, and that's going to be the mass over the MR. So our mass is 2.40 grams, and the MR, well, we got 1 times 24.3 for the magnesium. We have 1 times 32.1 for the sulfur, and we have 4 lots of oxygen in this molecule times 16.0. That gives us a total here of 2.40 grams over 120.4. If we put that into our calculators, we should end up with a value that looks like 0.0199 mole to 3 significant figures. Now, if we're going to do the next step, which is our mole ratio, to work out the moles of something we don't know about, well, we've got a 1:1 ratio here. So the moles of magnesium sulfate hydrated is going to be equal to the moles of magnesium sulfate times by 1/1, which in this case is going to be simply equal to 0.0199. And our final step here then is going to be to work out the MR, because we've got the mass. So the MR of MgSO4.NH2O is going to be equal to the mass, which we've found out here is 4.92 grams divided by the number of moles, which is 0.0199. And if we put that into our 4.92 divided by 0.0199, gives us an answer which is 247 0.24 grams per mole. So that's exactly the same as we've seen before. We're now going to go a little bit further and see if we can work out what the value N is in our water of crystallization. So, to find out the value of N, we know that the molecular formula mass of MgSO4 dot NH2O is equal to 247.24. That means we can find out the MR of the moles of water, and that's going to be the difference between the magnesium sulfate and also the MR of the anhydrous magnesium sulfate. So that is going to be 247.24, take away the anhydrous magnesium sulfate, 120.4, and we end up with a value for the moles of water, or the MR of the moles of water, equal to 126.84 grams per mole. And that is made up of a number of units of water. So how many units of water? N is simply going to be equal to the MR of the number of moles of water over the MR of water. So it becomes 126.84 divided by 18. And we should get a number which is close to a whole number. Indeed we do. 7.046, which is approximately equal to a water of crystallization where we have 7 waters per magnesium sulfate. Just a recap there then of what we've looked through. We've looked at calculating the relative molecular mass, calculating the number of moles in a solid, and then we've used these ideas to calculate the reacting masses and also the water of crystallization. Thanks for watching, and we'll come back soon.